So I will be talking about Bayesian optimization today, and usually I call it actually neuroadaptive Bayesian optimization because we're going to use it also on brain measures. But actually I wanted to broaden it a little bit and also present you some work we've been doing on behavioral data. So I thought that could be quite interesting as well. So in the next 15 minutes, I want to basically get you excited about closed loop approaches for cognitive neuroscience research and like what kind of potential they have. And I want to give you a feeling of the kind of research questions you can address with this kind of approach. And also show you some of the steps you can take, like give you like some kind of tutorial how to set up such an experiment. But also obviously to understand the limitations of the approach and when you can't use it. So why should we be interested in using closed-loop Bayesian optimization approaches in cognitive neuroscience research? And this is motivated by the fact that we as cognitive neuroscientists are interested in quite broad research questions, such as what are the fundamental aspects of cognition, what are the unique functional roles of distinct networks in the brain play, or how can cognitive processes be modulated or enhanced. And our standard approach in cognitive neuroscience is basically that we select two or a few task conditions a priori before an experiment takes place. We then test this on a cohort of subjects, like with mediocre sample sizes, and then we draw group level inferences. And what often happens then is that we write a paper or we make inferences based on these two conditions we've tested. So we would say a region X is like, for example, selective for condition A compared to condition B or so. But you see that there is actually quite a discrepancy between the broad research questions we're interested in and the kind of narrow experimental design we use. And this is just because this is how fMRI is being set up, and that we do need to pre-select a few conditions because of the costs and also the time associated with fMRI experiments. But I say that this in the past has led to a few problems in the field, one of them pertaining to human brain mapping. So this has led to overspecified inferences between function and anatomy. So for example, a classic example is the right inferior frontal gyrus that has been associated as like the seat of motor response inhibition, because it has always been tested in that way. But actually like now, basically also meta-analysis show that the right IFG is a region that is part of a bigger domain general network and actually has a much broader role in cognition than just response inhibition. And this is and another problem is, for example, for biomarker discovery, that we're still lacking very sensitive task conditions for which we know, for which we could, for example, dissociate a particular patient from a healthy control group. And this could be the case because they might be hard to find, but it could also be the case that we're actually not like looking broadly enough across the space of cognition. And another one is basically the confusion surrounding non-invasive brain stimulation. There has been a lot of controversy in the field if it actually works and when it works, and there are just like so many free parameters you can choose from that it will be hard to select the right ones that then work basically on a cohort of subjects or even on a cohort of patients that might be also that might also just have very individual anatomy and pathology. So all of these basically problems led us to think about another way to do a classic cognitive neuroscience experiment. And we thought about why are we actually like limiting ourselves a priori? Why we're not just defining a very broad experiment space to begin with, and then we're using like a machine learning algorithm to iteratively search through this through such a broad experiment space with the aim to optimize a certain measure. So this sounds all very vague, but just to give you like a really quick idea of how this works. So basically you would start with selecting like randomly one of these experimental conditions from this space. You then measure like a subject's, for example, brain response in response to this experimental condition. And then you see how does the brain look, and in which kind of way do I want to drive that brain? Like you need to define like a kind of target brain state here. And then you have like this machine learning algorithm, which is like Bayesian optimization, to do a quick and intelligent search through the space. So you don't have to test it exhaustively. But yeah, so now I exactly tell you how you could set up such an experiment, and I hope also that the whole approach will get a bit clearer in the following slides. So first, you have to think of a broad research question you could potentially not address in a classic kind of experiment. So in one of our studies, we ask what are the distinct functional roles two frontal parietal networks play in the brain and high-level cognition. And here the problem was that we wanted to do this in a closed-loop search approach, is because that these two frontal parietal networks are functionally very similar. So often they just co-activate for a diverse range of tasks. And it is very hard to predict a priori what kind of task conditions will, for example, dissociate them. And another research question we had was what are optimal brain stimulation parameters that would drive a behavioral response in the subject? And with brain stimulation, I think you heard a little bit about it today already, but I think you probably already can imagine that there are like many stimulation parameters like intensity, frequency, etc., or also where to stimulate. And that this leads quickly to a combinatorial explosion of experimental conditions that can't be run in a single experiment. So these were, for example, two research questions we were interested in the past, where we used this kind of closed loop approach. Okay, so maybe keep them in mind, because we're gonna come back to these examples, also like for the next step now. So the second step, after thinking of a research question you're interested in, you need to define your search space. The algorithm is gonna like basically look for the optimal conditions. So I call this like you need to parameterize an experiment space. And this is not a trivial task, because as I will show you in step 3, is that this approach works by a similarity assumption. So this means you need to put tasks or like task conditions into the space that you assume to elicit like a similar brain response. I will come to this back in a second, but you can do this like in different ways. So one way is to use prior knowledge of like how we know certain tasks, for example, activate certain brain networks. And in one of our studies, we have done this based on a meta-analysis performed by Thomas Yeo on fMRI data. And the nice thing was that he published like these kind of group masks, or like these masks of networks, of two frontal parietal networks. And he also published a posterior probability of many different cognitive tasks tapping into those networks. So what we did here, we spent like a two-dimensional search space consisting of a dorsal frontal parietal network and a ventral one. And now we aligned these tasks according to these probabilities. So you can see that, for example, here the Wisconsin card sorting task was basically predicted to elicit a high brain activation in this dorsal FBN and the low one in the ventral one. So you see the color coding is basically the contrast between the two networks. And then, for example, Posner and anti-saccade task, we would associate like with a strong activation in the ventral frontal parietal network and the low one in the dorsal one. So this was like a very neat meta-analysis we could use as our search space to search across cognitive tasks. Another one we did in the same study is to use intrinsic task dimensions. So that's another way how to define a search space. So you can look at like certain parameters you have in the task. For example, in the deductive reasoning task, we could play around with difficulty level and basically having first very easy like integration of problems that are basically just really where you have to solve like rules in parallel, and then they became more difficult when you had to like basically relate them in various different combinations. Or like in the Tower of London task, you could look at the number of steps you have to plan ahead. So these are intrinsic task dimensions, I call them. For the other study on brain stimulation parameters, here again we had another very easy to span experiment space because we can use intrinsic task dimensions. So in this study, we use transcranial alternating current stimulation, which is a method where you basically project or like use oscillations or sine waves, like you induce oscillations into the brain. And you can do this if you do it like with two independent stimulators. You can actually not just play around with the frequency of those oscillations, but also with the phase shift. So you can basically shift these oscillations in time. And as you probably know, is that we associate like these kind of time shifts also with how information flows through the brain. So that's kind of a neat technique to study this. Oops, sorry. But as you see, this was like a huge experiment space. We spun from like 0 to like 100 hertz, and then across the whole phase range from like basically 0 to 360 degrees in phase shift. Yes, so now once you have parameterized your experiment space, you can think about what is actually like your target measure. What do you actually want to look for? And again, there are many different ways you can do this. And one of them would be, for example, just a simple fMRI fold contrast. So when we were interested in dissociating two frontoparietal networks, we wanted to increase the fold contrast between them because we wanted to understand for which task conditions is one network active and the other one basically silent, and vice versa. So what we did is we used like real-time fMRI, and I also had like a slide really quickly about the pipeline because I thought it might be interesting because it's actually really easy to set up and really easy to run. So we had a Siemens Vario 3T, and here you can like really easily export the dicons in real time, and then you basically do all the pre-processing you would do usually. You do motion correction, you do smoothing. And in this case, for example, we had like two frontoparietal masks, and we just extracted the mean bold signal in those masks, and then you end up with two time courses. You can do like some more post-processing on them, you can de-spike them in real time, and usually for detrending, so for high-pass filtering, I just add like a linear trend regressor into the GLM. And then you basically, so this works in a per block basis. So what you do is you just have a GLM that grows in terms of time, obviously, and then also in terms of like the regressors you add to the model. And then what you feed into the Bayesian optimization algorithm is just this bold contrast. So it's really, really straightforward. Another way you can also optimize, and this is something I already touched upon when I opened this talk, is that you actually can also optimize based on behavior or preference ratings. So in this study, where we optimized across this brain stimulation space, we actually did not optimize on a brain measure, but we actually asked participants when they perceived phosphenes. So phosphenes are basically the flashing percepts you see under certain frequencies with TACS. And this is not a very interesting research question per se, but this was like a proof of principle study that you can do such an approach also for preference ratings. And then we hope to also employ this for basically behavior, that you could find out what are the optimal TACS stimulation parameters to drive accuracy up or to minimize reaction times or so on. And here in this case, so in basically this real-time fMRI approach, we optimize based on scalar values, meaning each condition, we just got a scalar and this one optimized for. And in this preference conditions, what we actually did was presenting the subjects with two blocks, and then we just optimized based on these binary judgment ratings. So this is another variant of this approach you can use, which could be potentially quite interesting. So then step 4 is you have to define your optimization procedure. And now we're going to talk a bit about the core element of this approach. What is actually Bayesian optimization? How does it work? So Bayesian optimization is a two-stage procedure consisting of the first step where you do a spatial regression. So you regress across this experiment space, and we're doing this using a Gaussian process regression. And then you close the loop, and that's why we call it closed loop, because the algorithm also automatically proposes the new experimental condition to be proposed to the subject in the next iteration. And there are two fundamental choices you have to make in these two steps. The first one, with the in terms of the Gaussian process regression, is you have to select the covariance function. So what does this mean? So a Gaussian process you can understand as an extension of a multivariate Gaussian distribution to a distribution over functions. So this means just like a normal Gaussian distribution has its mean and its variance, also the Gaussian process is defined by a mean function and a covariance function. And often for convenience, we set the mean function to 0, and then the Gaussian process is just defined by this covariance function. And this covariance function is really like the core of this Bayesian optimization approach, because it encodes like the smoothness assumptions in that space. So we often use, for example, a squared exponential kernel, and this really just means that, like if you see, for example, here, two different experimental stimuli, the closer they are together in that space, the more similar they will also look in terms of their brain response. And the nice thing about this smoothness assumption is that this is where the efficiency of the approach comes from, because once you've seen very basically unoptimal conditions, the approach will not look further in this same kind of region in that space, but move on and explore other regions in that space. So this is where basically the intelligent and the efficient search comes from this kind of covariance function assumption. But you can also choose like other kernels. So there are like many different kernels available, and you can adapt them to your research question. And just to give you like a short idea, like in 1D, so the experiment space would be like on the X now, and Y would be, for example, a bold response. So the prior, because you selected like a certain covariance function, basically before you've seen any data, you know that the space will roughly look that smooth. Now you observe data, so these are like your black points, and now you fit the Gaussian process regression. And now you see the space of possible covariance function is smaller. So because they need to go through the points you've observed. And the nice attribute now is that you're getting like this kind of mean, but you're also getting the variance of this of the covariance function. And this is really neat, because this is what we're going to exploit in the second step. So we basically know where do we expect high observations, and again, we want to optimize, so we're interested in these high end points. But we also want to know, for example, where the variance is really high, because maybe this is worth to explore. So in the second step, when we're proposing the new stimuli combination, we can choose among so-called acquisition functions. And there are different acquisition functions available, and they basically trade off the kind of exploitation or exploration you do. And I explain this in another example here, in this toy example. So, so here again, we have a 1D experiment space, like the same as before, and we have a bold response on the Y. Now, the black dotted line is your true objective function, meaning this is the one we don't know and we want to model. So let's say this is the response of the frontal parietal network for different tasks. Now, what we have is we have now two sample points in black, and now we fit a Gaussian process regression. This is blue. This is so-called our surrogate model, because we try to model the objective function. And as you see, we get a mean and also the variance, as I explained before. And now what the acquisition function is doing, it basically gives you the point where you can expect the highest improvement. So it looks, for example, where is the high predicted mean, but also where is high variance, and then let's sample there. Where do we expect the highest improvement? And so what we do is we maximize the acquisition function, we take the maximum, and then we sample from there in the next iteration. So here we sample, and now we refit the Gaussian process, and we do another, basically we run the acquisition function again, and we get another point where to sample from in the next iteration. And based on exactly the acquisition function you choose, you can see that you either go to, for example, points with high variance, or you go more to the points, oh well, only 2 minutes, to the points where you, sorry, I got a bit lost. But you see this in a very efficient and quick way. You can, in this toy example, you can model the unknown objective functions in this kind of way. The last step you have to do is to define stopping criteria. What I've done so far is to predetermine the number of iterations. So you say a priori, like, let's do 20 iterations and then finish. But you can also develop like really cool stopping criteria. For example, stop when enough statistical evidence has been accumulated. Just really briefly give you like a short video how this looks all when you take it together. Obviously, it's not a robot, but we just like to sometimes use it because it's basically automatic and the neuroscience being taken out of the loop. So here you see the subject is being presented with, like, for example, a random task in the beginning, flashing checkerboard. And now in real time, brain data is analyzed in response to this, and we see, oh, actually, the contrast between these two frontal-parietal networks wasn't that high. So let's sample from somewhere else in this space. So you see, like, we get like blue, so it's not really high degree activation. So now we're going like into encoding, show like an encoding task, and now we see, oh, this looks much better. And then the algorithm basically drops this kind of suboptimal space in the experiment space and moves on to this more optimal looking one, and then samples closely around this one. So this is where the efficiency of the approach comes from. When should you do this? Just really quickly. You should do this when you know exactly what kind of target measure you want to optimize, what kind of bold contrast you want to look at, what kind of multivariate pattern. You can use it also for connectivity or whatever, or behavior. You need to have all your pre-processing and analysis steps to be predetermined, but this is pretty cool and pretty neat because then you can actually also just combine it with study pre-registration. And I talk about this in a second. When the experiment space can be well parameterized, this is not always the case because sometimes dimensions are not known, or you can't be sure that the similarity assumptions encoded in the Gaussian process are not met. In those cases, you can't use this method, but you could use other active sampling approaches, not having Gaussian process, for example. And you expect moderate effect size because obviously you can't optimize across like really minimal contrast to noise ratios. For this, you can run simulations, and I always collect pilot data to also fit my Gaussian processes appropriately. Yeah, so we think it's kind of an exciting tool for cognitive neurosciences because in the end, you can, as I said, combine it with study pre-registration, but compared to like the common experiments you would pre-register, you can actually pre-register a highly explorative experiment, but still be protected against all these like p-hacking and all these experimental biases and wrong research practices that we're basically criticizing in the field. And this is because you are acquiring and analyzing the data at the same time. Yeah, so thanks to all my previous and also through current collaborators. And yeah, I'm happy to take questions.